All right. Hi, everyone. Welcome to VSPG. Today we're hearing from Dr. Dylan Wilmeth, a Mesoarchean oxygen oasis expanded, new trace elements and stable isotope data from the 2.8 billion year old Mosher Carbonate Steep Rock Lake, Canada. So let's see. I'm going to go ahead and introduce Dylan for us. So Dr. Dylan Wilmeth is a geobiologist who studies some of Earth's oldest carbonate successions, stromatolites, and microfossils. He combines paleontological expertise with a variety of geochemical tools to investigate questions related to the rise of atmospheric oxygen, life's response to mass extinctions, and how the oldest life became preserved. Dylan got his bachelor's from the University of Wisconsin-Milwaukee and his PhD from USC working with Dr. Frank Corsetti. His dissertation was titled Gas Production Within Archean Stromatolites, Evidence for Ancient Microbial Metabolisms. After his PhD, Dylan completed his two postdoctoral appointments in France at IUEM and the Paris Institute of Earth Physics. Sorry, I'm not good enough in French to say those in French. Today, he works at Grand Valley State University as a visiting assistant professor, continuous research, working on topics such as silicification in modern microbial mats, carbon isotope chemostratigraphy in the Loma Gundi Getuli aged Kona dolomite in Michigan, and applying iron isotopes and cerium anomaly to better understand redox conditions preserved in 2.8 billion year old carbonates, which I think we're going to be hearing about today. So we're really excited to hear about your work today, Dylan. So please go ahead.
Thank you so much, Alex. Thank you to UC Riverside for hosting me and all of these excellent talks. And thanks to you in the audience for sticking around, especially if you're around at 8 a.m. on the West Coast. Really means a lot to me that you're here. So as Alex mentioned, I'm going to be telling a story with a little bit of oxygen, a little bit of stratigraphy, a little bit of chemistry, and a little bit of life coming in together. As the intro mentioned, I find myself at the intersection of all of these techniques combined. So without further ado, one final note, this is research from my second postdoc in Brest, France at IUEM with Stéphane Lalonde. We got a large European Research Council grant for this, co-funded also by Phil Fralick at Lakehead University. So now without further ado, let's dive in. There we go. Perfect. So one of the largest questions in Precambrian history, in Earth history, is when did oxygenic photosynthesis originate? The how is fairly well understood, broad brushstrokes. Life makes oxygen, whether it's cyanobacteria or perhaps some early precursor. The focus of many studies now is when exactly it evolved and when it started to change the Earth. So there is sort of a spectrum of hypotheses, but you can broadly clump them into two major families. The first is around 2.4 billion years ago, we see clear evidence for red beds, for changing sulfur isotopes, changing uranium, a whole litany of geochemical and sedimentary evidence that we have a more oxidizing atmosphere. Now, hypothesis one is that it didn't really take a long time for oxygen to ramp up, that essentially the GOE represents the onset, the advent of oxygenic photosynthesis. Hypothesis two instead postulates that photosynthesis producing oxygen has been around for a lot longer, perhaps for hundreds of millions of years. Now, in this case, oxygen would affect local environments, as we will see, but was buffered out by reduced carbon, by reduced iron, reduced sulfur, the list goes on, so that it did not quite affect the atmosphere to the effect that we see in the GOE. So these are the two major camps. And today we're going to be testing out hypothesis two, testing out to see if there are pockets of oxygen beforehand. Now, this has been studied in intense detail. Where are we looking for? If we're looking for oxygen production, we can't just look anywhere. Since it's made by life, we tend to look at microbial colonies, or at least local environments where they are existing, which is perfect for me as a stromatolite nut. It means I can focus on these guys. There's a term that's been thrown around for several decades called an oxygen oasis. This idea is that you have localized oxygen accumulation in a relatively restricted zone surrounded by the big bad Archean anoxic atmosphere or water columns. Now, we can see analogs in modern situations. Don Sumner and company have a series of beautiful papers looking at Antarctic lakes. Now, water at the bottom of these lakes is fairly low in oxygen, but these beautiful mats, some tufted, some plain, there's a whole variety, contain very relatively high concentrations of oxygen that then diminish. So this is an oxygen oasis in the smallest sense, in the mat sense, centimeter scale tops. And we can see these centimeter scale oxygen oases in stromatolites. My most recent geology paper discusses this in more detail. This is a previous study looking at stromatolites from about 2.7 billion years ago from lakes in the Fentersdorp supergroup. And here we not only see textural evidence for gas production, such as bubbles and fenestrae that we can see here, we see chemical evidence, such as primary iron oxidation, and we see cerium anomalies associated with these. We're going to talk more about cerium later, so I'll just leave that at the door for now. But again, this is on millimeter centimeter scale. Today, we're going to examine larger scales, longer time frames. Don't worry, we are going to be looking at stromatolites, so if you're here for that, you are good. But we're also going to be looking at larger processes over the evolution of an environment over time. So with that in mind, there are many places to try to look for these. My sort of wheelhouse for the past few years has been lakes. But this postdoc project looked at a different environment, early carbonate platforms. And I love this picture here. Carbonate platforms come in a variety of sizes and shapes, but broadly, you have a relatively shallow, relatively more restricted environment that is separated, not completely, but separated enough from anoxic open oceans. Just imagine this as the big bad Archean Ocean surrounding our little natural laboratory here. And in these shallow waters, oxygen production from photosynthesis could locally overpower these massive redox buffers. As I just mentioned, it could be a natural laboratory. Here's a cross section through such a platform. This is modified from Riding et al., who's a co-author on this. Again, the oxygen oasis we'd expect to be on the platform top, suboxic, whereas any distal deposits would be anoxic and probably saturated with that reduced iron, Fe2 out there. So we'll come back to that picture many more times going forward. Great. We want to look at an early oxygen oasis, or we're trying to find evidence for them on carbonate platforms. Also from Riding et al., these are carbonate deposits over time. There's a cluster in the Paleoarchean that don't get much more than a few dozen meters max. But in the Mesoarchean here, we really start to ramp up with the Pongola group, and we also start to reach this, the topic of our talk today, the Mosher Carbonate, 2.8 billion years ago. It's one of the earliest major carbonate deposits. You might know it more familiarly as steep rock or steep rock lake in the literature. That's the typical shorthand. But the technical stratigraphic definition here is the Mosher Carbonate. So I might just off a hand talk about steep rock or Mosher. If I do, that means exactly the same thing. So it's not as thick as these thick Kambarand-Malmani deposits later, but we will get into some comparisons soon. So here's the time, here's the place. Let's look at the layout a little bit here. So there's the preamble. What are we going to do at the Mosher Carbonate? I'm going to set the stage first. We're going to look at Mosher stratigraphy. There is more than a century of work here that I'm going to boil down to a few key features. I'm also going to briefly talk about cerium anomalies. If you are very well versed in cerium anomalies, that's wonderful. If you're not, I'm going to walk you through how the technique works, some of the pitfalls and some of the benefits. Then we're going to look at studies about 10 years ago, again done by Rob Riding and Phil Fralick. Then we're going to focus on 3 points of data. We're mostly going to focus on new cerium anomalies here. If you've seen, I just gave a GSA talk on this, but I can expand it more here. We'll see how our new data set expands and complements previous data. The second point, we are going to produce the first iron isotopes from carbonates, from calcium and magnesium carbonates here, to learn how iron was being recycled or cycled in these zones. And then very briefly, I only have about 1 or 2 slides for carbon isotopes. How did microbial communities react to all these changes that we'll see? So let's start by setting the stage. As I mentioned, the Mosher Carbonate is about 2.8 billion years old. We're in the southwestern Superior Craton. A lot of information on this left-hand chart. All I want you to know is that steep rock here, the Mosher Carbonate, is the green star. Our ERC research group is also focusing on other locations in Red Lake and Woman Lake, so keep your eyes out for those for maybe future talks, but we're here for now. The Mosher carbonate is exposed in relatively thin strips squeezed between tonalites and metavolcanic rocks. The Mosher carbonate here is in blue, but most of the work has been done here. And these dots are on 3, 4, 5, and 6. These are the best exposures. This exposure has a very, very rich history. And to start off with a slight tangent, I believe, based on a lot of literature research, that these are the first or the earliest described Archean stromatolites. So in 1912, Charles Doolittle Walcott visited this quarry and found beautiful stromatolites. And he didn't know they were Archean. I'm not even sure if the word had been invented then, and I'm not even sure he knew they were stromatolites. But if you trace the roots back, this might be the very first description of them. Again, Walcott gets a lot of credit for the Burgess Shale. I think we should also laud him for his Archean work here too. But for our story, it really begins in 1944. These large lakes were drained when they found iron formations around, and all the mines were elsewhere on the lake. But at this corner here, they uncovered more and more and more carbonates, up to 200 meters, including the poster children for the Mosher Carbonate, these giant domes. If you've ever heard anything about the Mosher or Steep Rock Lake, you've probably heard about these domes. Here's a cowboy hat for scale down here. We're going to get into those domes in just a second. We're going to slice them open like an onion. But let's look at the stratigraphy. Fortunately for us, there are only 2 members. There's the lower Hogarth member, and then there's the upper elbow point member. So who's where? I'm going to have a stratigraphic column on the left here, Hogarth below, elbow point above. I'm just throwing these here because I always get this question as far as mineralogy. It's mostly calcite here. Pardon me, there is some dolomite, and we will see evidence of replaced aragonite. That's not going to factor too much into our story here, but I'm just going to cut that question off at the pass. I'm using different color codes for different features here, and I'll remind you which is which as we go forward. The Hogarth member has a beautiful, diverse assemblage of microbial textures. We have the classic domal and laminar stromatolites here. We have some interlayering between dolomite and calcite here. We got a nice Canadian penny for scale. The penny is about the same scale for these beautiful finger-like columnar stromatolites. Now, those only show up about here in the middle in brief intervals. Those are more dolomitic. And then there's an interval near the top that they're not quite stromatolites, but they definitely show evidence of complex fenestral textures. I've mentioned fenestrae before. If you haven't heard that word, it is simply a primary void space inside a microbialite or sediment. It was either built by expanding gas, or it might have just been a void filled with water. But there's a lot of them there. And the textures do appear very, very microbial. Now, you might have noticed there's 2 red bars here. And throughout, but especially in these deposits, we get extensive crystal fans. Now, everything I mentioned before is biological. Crystal fans were not directly made by life. This is a fairly established fact in petrography and in geobiology. These are former aragonite precipitates growing as you supersaturate carbonate on the seafloor. Don Sumner published on these. Here's one from Fralick Riding. And if those aren't very clear, here's a classic cartoon of what these look like. They're growing off of the seafloor. Again, can't emphasize this enough. The structure we see here is more from supersaturation than life itself, as opposed to those beautiful crinkly stromatolites. Moving on up, that's the Hogarth member, a diverse assemblage. The elbow point member is weird. It is only giant domes. They are sitting on top of each other with very little interstitial sediment in between. The location of these giant domes has been debated. I'm not going to sugarcoat that. Some people place them deeper in the water. Some people place them closer towards a platform margin. We tend to think of them as margin deposits. We think the chemistry sort of backs that up, which we'll see in a second. Here's some hats for scale. They're up to 1 meter high. They're up to 4 meters wide. And they're complex structures. This image on the right is a natural cut through one of the domes, and they really look like slices through onions. So what we're going to do here is just take a slice here. 3 distinct layers. Again, color-coded. They usually form in patterns starting with non-fenestral microbialites. So imagine those microbial mats we saw in Antarctica. Imagine the more denser, flatter versions. They're just a bit thicker. Then we get fenestral microbialites. They have a more open framework. Some folks call this chicken wire texture. Imagine these as sort of those cones that are sort of poking up through, like we saw in Antarctica. And then, again, a little bit blurry, but you can see here some of these spikes radiating out. We have crystal fans growing up, through, and out of these fenestral microbialites. And we see this happening over and over and over again. There's a little bit of play here, but typically you go from non-fenestral to crystal fans and repeat again. One final note here that we're talking about fairly fine centimeter scale changes between these layers. So we've got our large stromatolite-rich platform below. We've got our big domes above. What are we interpreting this as? If I were to swim in the Mesoarchean Sea, what would this look like? The Hogarth member is traditionally interpreted as platform facies and flooding over time. I didn't mention it here, but the very base of the Hogarth has beautiful sandstone deposits that quickly get overturned or overlain by carbonates. So there is evidence for flooding, for gradual sea level growth during the Hogarth. The elbow point, things change a bit. We believe that, or we interpret the elbow point member as marginal reefs between the platform and the open ocean. I'm going to show more evidence for that in just a second, but if anyone has any alternate hypotheses, happy to talk about them later. But that's where we're going to put them for now. There's the stage. What were the redox conditions then? What was it like during the Hogarth? What was it like during the elbow point? How did it change? Was there any change? And how do we know? So for this, getting a bit into the nitty-gritty of chemistry. So we're going to be looking at cerium anomalies. Now, the straight ahead way to write that is CE divided by CE star. I'm going to show what that means right now. If you're not aware, cerium is a redox-sensitive rare earth element. This is a classic sort of chart with all the rare earth elements. We don't need to know most of them, but I really want you to focus here. Cerium is the second one from the left. Its neighbors are lanthanum, La, and praseodymium, Pr. I'm usually going to use those abbreviations just to save some time. And broadly, if I have a limestone or a dolostone and I look at rare earth elements across the board, they're relatively reliable proxies for seawater rare earth elements. There are some kinks that can happen if you want to talk about later, happy to do so. But broadly speaking, carbonates provide a snapshot of ancient rare earth elements. The important thing I want us to remember here is that Ce is more redox sensitive than its neighbors. So redox reactions, oxidation, reduction, are going to change cerium concentrations, and it's going to do so more than its neighbors. So if we see more cerium than its neighbors, that's going to be a positive cerium anomaly. In contrast, if there's less cerium than its neighbors, that's a negative cerium anomaly. We're mostly going to be talking about negative here. Let's look at what exactly that means and how we can change this. All right, so if I took a cup of most modern marine water, I would probably see a negative cerium anomaly. It's oxidizing, it's oxygen rich. Oxidized cerium 4 binds to oxides, usually iron and manganese oxides. Those oxides sink and are removed from the water column. The more is sorbed and removed, the less cerium is in the water column. So that's our classic negative cerium anomaly. Now, all that cerium's got to go somewhere, though. And if we cross a redox line, if we start to reduce all that iron, that cerium is now liberated. And we now make a positive cerium anomaly, a water that is more rich in cerium. Again, we're not going to talk about this too much, but it's good to know the two sides of the coin. Now, this is the basics. There's one other wrinkle I want to talk about here, and it is important for how I'm showing cerium going forward. Okay, there is a way to make for me, I can't think of a better way to say it, a false cerium anomaly. So here on the right is the classic version I just showed you. Here's cerium. It is much lower than lanthanum, much lower than PR. That is the classic signal of oxidation. But in some places, you can see that a cerium anomaly can be formed by raising lanthanum, but not touching cerium at all. This is mentioned in Bao and Dulski, 1996. This typically occurs as lanthanum increases, and this typically happens in more open marine environments. There's a lot more to it than that, but we're going to keep it there for now. The one on the left doesn't really tell me about oxidation, so that's why I'm calling it a false CE anomaly. So how do we address this? How do we tell the difference between the two, besides looking at this here? Well, we can compare cerium and PR, praseodymium. So in my oxidizing conditions here, not only do I have low cerium, my praseodymium is higher, roughly speaking, than the sum of its neighbors on average. Whereas over here, it's a straight flat line. So here's how we show this on charts. So here's our classic CE over CE. Again, PAAS, if that ever comes up, it's just normalized to Archean shales. That's the bog standard. And then here's our PR, our praseodymium anomaly. So in short, and I've kept these squares here for a specific reason. Typically, if I have PR over 1.05, that's typically interpreted as a true cerium anomaly. I can only get that PR value if I'm removing cerium, truly removing cerium. Whereas anything over here is more reducing. Going to still call that the false cerium anomaly. And I'll keep this color code on. Blue for oxidizing, brownish for reducing. Okay, so kind of bringing it all back home. What does that mean for this talk? I'm going to be plotting PR over time as a sort of belt and suspenders way to check our cerium anomalies. Cerium alone is not enough. We need this. I will be using quote unquote cerium anomalies at the top of this chart just to sort of avoid any extra confusion with PR and CE. So if I'm mentioning a cerium anomaly, I'm really using a combined CE and PR and showing PR here. It's a bit easier to show with stratigraphy. Hopefully you'll be able to catch the drift as we go forward. One more time. PR in the 1.05 or above, that's oxidation. I'm going to call that a negative CE anomaly. Anything over here is going to be reducing conditions. With that in mind, let's look at previous data. All right, so this is work that Rob Riding, Phil Fralick, and others did 10 years ago in 2014. Again, I know there's a lot of different colors here. I'm only going to mention the colors specifically when they matter, when they come up. Pardon me. Now, without even me putting words on the screen, we can see some trends here. We can see that the Hogarth member is, broadly speaking, little or no cerium anomalies at all. These are interpreted as relatively reducing zones. we're still on a carbonate platform, but as we're flooding over time, we are influenced by an anoxic basin around. No real oxidation here, nothing in the blue. All right. All right. So then why do we consider this an oxygen oasis? Well, what Riding et al. Found was that the giant domes did have oxidation. They found some in the fans, they found some in the fenestral microbialites. There's a little bit of play here. So simply put, they found that these elbow point domes, they thought there's probably some sort of separation between oxidizing conditions closer to shore, or at least on the platform, and our anoxic basins out here. So what we're going to do, we're going to produce some more cerium anomaly data. We're going to go through the Hogarth, and we're going to produce a lot more in the domes, and we're going to see what's changed. So again, at the moment, as of now, Seabrook is considered to be a limited oxygen oasis. What's our new data tell us? All right, so there are three important trends. We're going to start from two from the Hogarth member and one from the elbow point member, but they all combine together to tell a story. Starting with the number one. All right, in the Hogarth member, we see this trend. This is our new rare earth element data. And if you think, well, that looks pretty similar to before, you're not wrong. But we do see a more pronounced trend over here to the left. Now, I've thrown a lot of chemistry at you, but to remind you that the more we go in this direction, towards the left on this chart, we are getting not true cerium anomalies, but those false cerium anomalies, enhanced lanthanum over time. So check these out. More lanthanum, more lanthanum, more lanthanum, all the way on the far left. Cerium is not really dipping down too much at all. I briefly mentioned back then that lanthanum typically increases in more open marine, or at the very least, less restricted zones. And we have two other proxies that match this well. It's fairly well established that Archean oceans are very iron rich. Here we have iron concentrations increasing, increasing, increasing as the platform is being flooded over time. Now this is some new data here. We also have new yttrium-holmium ratios. Again, in a nutshell, the more yttrium to holmium we have, that is classically less restricted, more open marine influence over time. Yttrium increases, iron increases, lanthanum increases in its unique way on this chart. I think these three chemical conditions are a pretty good indicator, plus the sedimentology itself, that we are gradually flooding or drowning our platform over time. So again, a relative sea level rise. Not quite sure if it's the basins, the platform sinking, or perhaps more likely sea level rising, but you get the idea. No oxidation yet, but I will admit I've hidden some data points from you. So let's show them now. What I'd like to show you, these are the first true negative cerium anomalies reported over here. They fall solidly in our oxidizing zones. They only appear about twice on the platform, and they only appear during crystal fan deposition, which might seem weird. I glossed over it at the beginning, but we think of oxidation, or at least oxygen production, if we're going that far, as microbially induced. We're looking at microbialites in the first place. So what gives? Why are we finding this intense cerium oxidative signal in the microbialites, even though they are not built by microbes? And this, we're still working on a hypothesis. I'm very interested to hear what y'all think, but here's my going hypothesis for the moment. That whether these were in benthic mats, or maybe there was some blooms in the water, but we'll just say benthic mats for now. There were conditions that really fostered oxygen production, or at the very least, CO2 removal. The more CO2 you remove from your water, the more carbon fixation is happening, the more likely you're going to supersaturate your water with calcite, or in this case, aragonite. The more you remove, The more supersaturated you get, the more you're going to foster rapid crystal growth. Now, several studies have hypothesized about the rates of crystal growth. It's generally assumed that these types of fans precipitated faster. And so our idea is this. Because we see oxidation signals, we're going to say here that oxygen production removed CO2. That cascaded into supersaturated environments, we grow rapid crystals. And these rapid crystal growths can record these transient CE anomalies. Maybe over here, maybe they're making oxygen and we just haven't looked more closely yet. But maybe these conditions, again, I cannot stress enough, the fans themselves are not built by microbes, but microbes are setting the stage for these to be made. They're basically making these gardens, one might say. All right, so really cool. These have not been reported from the Hogarth before. That is brand new data. Let's look at the elbow point member. This was the member that was used as the poster child for oxidation in 2014. But we found some even more detailed data. We focused on these three layers: non-fenestral, fenestral microbialites, and fans. And there are clear differences between these layers on a centimeter scale. Non-fenestral mats, microbial mats just sitting there doing their thing. Very closely resemble Hogarth mats, just sitting there doing their thing. Higher lanthanum, normal cerium, that is to say it has not been depleted from the water. So we are saying these are reducing conditions here, similar to most microbialites over time. It makes sense. They're their closest cousins texturally. Moving on up, most fenestral mats have negative cerium anomalies. So we're interpreting here, this is mild oxidation. They're oxidizing, but they're just kind of over the border. This is what Riding et al. Published about 10 years ago. The crystal fans. If you might remember, crystal fans were distinctly oxidizing 10 years ago, and they formed their own almost distinct unit here. And even more interesting, I think, is that they have the same relative overlap as crystal fans much, much earlier. Not to speculate too much, hundreds of thousands or likely millions of years earlier, they fall in that same ballpark. And again, to stress, especially say in this bottom line here, the difference between that brown dot, these blue dots, these red dots are only 1 to 2 centimeters apart. I'm not going to speculate too much on rates of growth, but I would feel comfortable saying that these shifts in oxidation are occurring more rapidly than the shifts that we're seeing in the Hogarth below. More detailed sampling needs to be done, but that seems to be the case for now. So, as I just mentioned, relatively rapid scale changes. And we think that this kind of solidifies a margin interpretation. To quote Steeler's wheel, these elbow point domes are stuck in the middle. They've got more oxidizing conditions. Even if you don't want to call it an oxygen oasis, we see clear evidence of an influence of oxygen production. These fenestral mats, these fans that are growing. Whereas these anoxic basins, when water is flowing in, we clearly see the same type of flat or crinkled mats that we see earlier on in the Hogarth. I've shown these charts before. These are our iron-rich oceans increasing in the Hogarth, and we see our yttrium-holmium increasing in the Hogarth. This was the flooding story. What does this look like in the elbow point domes? Iron concentrations drastically decrease back to basically where we were at the very beginning of the platform. Yttrium-holmium ratios kind of stay a little bit steady, but note that our more oxidizing facies, our blues and our reds, our fenestral and our fans, are in the less open ocean section over here. Not as clean cut as cerium anomalies, but pretty dang close. So that's the sort of ending point of my cerium story here. I like using this as a bridging point because our next topic is going to be iron. But just before I go, old cerium data showed an oxygen oasis. Ours showed that that oasis was present for punctuated times much earlier than we thought before, and we see clear trends in the scales of these giant microbialite domes, or mixed structure domes here. We can look at trends like flooding over time as well. All right, so these next two sections are going to be a little bit shorter, but we'll spend some time on iron, specifically iron isotopes. All right, changing gears a bit. Just as rare earth elements are usually incorporated into carbonates with little or no change, the broad consensus is that iron is incorporated into carbonates with little or no fractionation. Experiments seem to support this interpretation. Now, the main source of iron we're interested here in the oceans is hydrothermal. When iron belches out of a black smoker, or at least belches out of black smokers back in the day, it's interpreted as around zero. We're going to leave it at zero for now. A lot of changes we will see in carbonates go in the negative direction. And so they're interpreted as primary or maybe very early diagenetic changes in time. So what do we see in the Mosher, and what is it telling us? Well, I want to set you up with two contenders. There are many different ways to do this, but again, two broad camps. If you have other ways to make light isotopic iron, I'm all ears. I will admit I'm a little bit newer to this side of the game. So the first is the classic plume model. We have our HT hydrothermal systems. This is taken from Andy Chaya, and that reduced iron is eventually oxidized. Might be from oxygenic photosynthesis, might be from some anoxic process, just some other oxidation. In either case, we remove heavy iron. And the residual iron that's left, that little fraction, is increasingly depleted. The other alternative is dissimilatory iron reduction. I'm just calling that DIR from here on out because most people do. In this case, iron-reducing microbes are producing more Fe2, are making more reduced iron, or converting is a better term. Now, interesting to note that it still requires a source of somewhat oxidized iron for this to happen. So already we're getting into the complex nature of this. I'll show you what this will look like on the Mosher Carbonate in just a second. But before I do, I'm just going to show you the data straight. This is an excellent review by Aroglu et al. 2018. Note that igneous rocks and most hydrothermal systems fall right around 0 per mil. That's the bog standard. The circles here are calcium magnesium carbonates. We're not talking about siderite. We don't really see, we did XRD, we saw no siderite in our formations at all. So that's a whole other can of worms. I want you to note here around 2.5, just before the GOE, a massive amount of negative values. Think of the Camporan-Malmani platform, think of the Western Australian platforms. So we're going to fill in a gap right here. There's some, I believe, from the Pongola. I forget exactly where, but here's where the Mosher Carbonate fits in. Not only is it much more depleted than anything else that comes before, caveat that there's not much that comes before, it's more depleted than anything else at the same time, and it falls very closely within ranges of our iron isotopes here, say in our more classic large later Archean deposits. So just as has been asked in South Africa, in Australia, is this a plume? Is this DIR? Or is this something else? All right. So just like I showed cerium over time, let's look at iron over time. And there are two broad trends we would expect to see. Remember, in a plume model, iron is introduced and then slowly winnowed away. We're removing heavy iron, and the fraction remaining should have less or depleted iron isotopes. So if we see any depletion in iron isotopes, we would expect to see a depletion in iron concentrations as a whole over time. Less iron, and it's lighter. Now, DIR is different because these microbes are converting more iron too. They're making more and more of it in the water. So I believe I've got this paragraph a little bit backwards here, but in short, I would expect to see higher concentrations of iron in my water with lower with depleted iron isotopes here. So with that in mind, we should see two clearly different trends. What do we see? Let's start with the Hogarth. Remember, this is our flooding platform over time, rich in microbialites. Broadly, we see a decrease in iron isotopes from around, but we're already starting pretty close to -1 here, note off, but we go from -1 to -2, depleting over time. Meanwhile, iron concentrations are getting higher and higher and higher. If you remember from my diagrams, we see more encroaching oceans here, especially around after 40 meters. I will note that there's one little sitch here where we go decreasing iron concentrations. So there could be some oxidation here in our crystal fans. I've noted our oxidizing zones here in gray. Not so much down here, but possibly some minor oxidation there. It's more data would need to be collected to confirm. Elbow point member. Our iron concentrations are drastically depleted, and our iron isotopes remain around similar. We don't see the same beautiful trends in beds that we saw, but I would say broadly, less iron and it is depleted would be more similar to a plume or iron oxidation. Again, by itself, maybe not evidence for oxygen, but plus the cerium anomalies, I would think provides a pretty decent 1-2 punch. One final comparison here. Again, I don't have this cited, I apologize. This is also from, I believe, Aroglu et al. 2018. That team's work looked at iron and isotopes on the Kambaran-Momani platform. The larger boxes are not quite to scale, but the dashed lines are. Most of our data from about 300 million years earlier falls around -1 and 0.5 ppm. That same box over here falls within range of what they interpreted as subtidal and paratidal conditions, restricted interactions with an open ocean. There is more influence from diagenesis and continental fluids. I'll say here there's no clear evidence for most of this of a proximal detrital source, maybe at the very beginning, but I think it's shallow. We're probably close to some shoreline. This fits. We're restricted isotopes. All elbow point domes are like this, and most Hogarths are like this. But it should be noted that some of our Hogarth carbonates way out here fall off that trend. There are more iron enriched in these samples. In Aroglu and company's study, they interpreted these as more of a slope trend, that these were interacting more with ocean water, that there was a chemocline here, which makes sense. Remember, these are where we are starting to flood our platform even more, whereas our later deposits in the elbow point are more restricted. So comparing ours with once hundreds of millions of years later, there are not a lot of platforms around this age, but the ones that we do see are a foresign of the things to come hundreds of millions of years later. So again, just a broad overview, summarizing everything I've mentioned so far. We see highly depleted isotopes, hundreds of millions of years before the GOE, and similar platforms later. They resemble these Neoarchean carbon platforms. Mostly a paratidal influenced restricted basin with more influence of DIR during platform drowning, but more likely oxidation during these domes here, again, in that especially restricted area. So the iron isotopes, and the sedimentology all beautifully weave together to tell a story. Last but not least, or I hate to say least, but maybe a little bit, our carbon isotope data. How did microbial communities react to these changes? We've seen flooding or drowning of the platform. We've seen changing influences of iron isotopes and oxidation. So you maybe would expect to see major changes in carbon isotopes. Not really. Most of our samples plot very boringly between -25 to -28. So that's for organic carbon, I should say here. Inorganic carbon isotopes are straight at between 0 and maybe slightly positive or negative, but as you would expect for a carbonate. So with that difference around, again, minus 25 to 28, that's classically touted as the Calvin-Benson cycle. I am very aware that there are many ways to make different organic isotopes. So if you have any other alternatives, I'm happy to hear it. More importantly, there are no clear correlations between redox chemistry and carbon isotopes, maybe a couple, but again, like the fans, I'm actually kind of surprised the fans have any organic matter at all. I think those would be very, very low concentrations. There are no major shifts with the redox chemistry that we can really see here. Maybe one weird lump down here, perhaps methane cycling during drowning. Okay, so maybe there's a little bit here, but it's if you want to talk more about that, happy to. That's kind of tacked on at the end. It's a little bit more of a recent data set, so hope you'll forgive me for that. So that's a lot to throw at you, but here are broad conclusions, weaving everything together. It was interpreted as an oxygen oasis 2.8 billion years ago, the Mosher Carbonate platform. That's around 400 million years before the GOE. What we have is fleshing out, expanding this idea, and still confirming it. Negative cerium anomalies occur throughout the platform, including the first from lower facies in the Hogarth member, especially in crystal fans. We are interpreting these tentatively as punctuated oxidation. The more oxygen is the more oxygen is made, the more CO2 is removed. That CO2 fosters extra carbonate precipitation, that removing, I should say. Looking at iron isotopes, we see a potential mix of oxidation and DIR influence, but they make sense where they lie. Iron reduction, when we have a lot of iron-rich ocean soup for them to munch on, and oxidation in the more restricted conditions. And I'm a sedimentologist that is my background, although I would consider myself a geochemist after all of this. I'm getting there. But from a sedimentology, geobiology, and geochemistry perspective, the stories appear to match each other very well. Initial flooding, followed by restriction, oxidation in certain specific influences on the platform. So with that in mind, thank you very much for listening. I will take any questions that you have. I want to thank the Earthbloom team with our ERC-funded grant. And again, thank you for sticking around. So I'll take any questions.
All right, great. Good talk, Dylan. Thanks so much.
Thank you.
Just as a warning, you probably already know we don't really stop the question session until there are no more questions. So let me know if you need to go sooner than later.
Fair enough.
So you can ask questions in a couple different ways. You can raise your hand by the reactions button, or you can type your question into the chat and I can read it aloud for you. I have one in Mike Zawoski has his hand up, please. Good to see you, Mike. Please go ahead.
Hi there, everyone. Hi there, Dylan.
Hi, Mike. Good to see you.
Thanks again for your really interesting talk. The big question that comes to mind in the bigger picture of this is trying to make sense of, are these variations in the chemical data you see indicating this difference in kind of diluting of the microbial signature, or is this changes in some microbial metabolisms that are happening during this time?
Yeah, this is a question I come back to a lot, Mike. I completely agree. Just to rephrase it, and you can tell me if I'm wrong here. I usually think of it like as, is oxygenic photosynthesis happening the whole time, and we are just capturing like certain periods where it's more likely to be captured, or are we really seeing like dead zones of oxygen and then, real like hot flashes of it? I guess my gut is that there's probably pervasive, maybe very low level oxygen production throughout. Why it would start to fluctuate up at these specific points in time, I don't have a specific reason for that. Maybe there's an influx of nutrients. Maybe we can go and look at different parameters for that in the rock record. Or yeah, long story short, if you asked me, and you can let me know if there's anything more specific you want to ask for that, I think it would be that we're probably seeing changes in the overall production of oxygen production that is probably there low lying, but something's causing it to fluctuate. I think the fact that we see these fans, we don't see fans everywhere. We see fans only at certain points in time, which means that there must have been some boom time for oxygen to really benefit. I guess another question is why why then would oxygen be so limiting the rest of the time? So again, that's a next step that we'd love to take in short.
Yeah, thanks for that. I'll need to process that some more to think about why we see the kind of regular alternations over such a small scale, and thus how that would relate to sea level. So was there some just consistent accommodation space generation that allowed things to stay in this photic zone and to match this deposition rate? But at the same time, why would we have, why wouldn't we have this cerium anomaly stick around if the oxygen is always being made? I could see the variations in the supersaturation, kind of omega for carbonate deposition, but then it seemed like if oxygen should be being produced the whole time during that, yeah, it's hard to tease it all together. Just, yeah, so that's the kind of thing I need to process. So thank you for that.
I have one more follow-up to that. One thing I didn't really mention here is that iron by itself is typically an inhibitor of calcite precipitation. I forget about aragonite. I used to know that, but typically it's seen as an inhibitor on surfaces. So not only, if I'm just spitballing here, not only would oxygen production remove our CO2, if we are oxidizing iron and removing that from the equation, it could be a 1-2 punch. We're removing this chemical inhibitor of calcite precipitation. That might also be a factor of why it's very punctuated, potent bursts of it. So that factors in too. If there's nothing else there, I see Robin has a hand. Good to see you again, Robin.
Go ahead, Robin.
Yeah. Hi, Dylan. Thanks a lot for the talk. It was nice. To jump on the previous question, actually, I was wondering if you could explain or what you think about a possible explanation of the fact that you record the cerium anomalies, oxidation, only in the crystal fan.
Yes.
Could be related to the flooding and not flooding conditions. If you imagine that crystal fans tend to precipitate due to oversaturation, and oversaturation often can occur if you isolate your basin. And let's say when you're not flooding as much as you are during your first trend, as you're showing like the stronger connection to the ocean, you imagine you stop that connection and then you increase your saturation indexes, and then you precipitate your crystal fans. And even if you have a constant oxygen production with photosynthesis, then you could possibly record your cerium anomalies because you have less reducing buffer. Rather than increasing the oxygen production, you could have constant oxygen production, but less buffer due to disconnection of the ocean platform. I don't know if that's what you think of as well.
Yeah, sorry to interrupt. I absolutely agree. And if you have seen me give this talk at GSA and maybe some earlier rough versions of this, that is exactly what I have said in the past. The reason that I would still completely agree with that, and I think in some situations, especially the elbow point domes, I think that's a very real possibility, seeing that paratidal influence in many factors. Reading more into the fan literature, again, my background is stromatolites, so I was like, oh, what are these fans doing here? But then when they had the cerium anomaly, it's like, okay, let's learn a bit more about them. This might have changed over time, but I know that a lot of Don Sumner's work on these fans and others show that restriction is one way, absolutely, to get fans, but we also see them in facies where there does not appear to be any extra restriction, either shallowing or otherwise. I forget exactly, like there's the Bulawayo, they talk about a whole bunch of different facies in different places where in those spots, restriction does not seem alone. Restriction alone is not enough. And I think that restriction might work for the elbow point domes that are more restricted, but for our lower Hogarth ones, they appear up a couple times. And because we're gradually drowning, maybe there's extra restriction there, but maybe in those relatively deeper zones, or at least less proximal zones, that might be more towards the metabolism itself. Long story short, I think it's absolutely a combination of the two.
Do you have oxygen isotopes in the, sorry to interrupt, do you have oxygen isotopes in the carbonates that could like show
I do.
like this kind of evaporation thing?
You're absolutely right. We do. I don't remember. I haven't looked at that in quite a while. It's been a while. I don't remember them showing huge correlations, but that would be a great place to start.
Thanks.
Thank you.
Okay, Dylan, there's one in the chat from Karthik Sender Sarwan that says, thanks for the amazing talk. What factors drives the periodicity between repeating non-fenestral, fenestral, and crystal fans in the domes? And does the angle of the elbow point further influence the hydrodynamics, especially considering the yttrium-holmium ratio shifts from Hogarth to the elbow?
Yeah, let's see, I'll answer the last part first. Um, let's see, I'll come back to yttrium holmium. The long story short with the yttrium holmium and all of these others, here we go, right here. Okay, great. What I'm not showing you is that there's a decent gap here between our 120 and 160. This is a more conservative estimate for this gap. If you were out there in the field, and I'll admit that I have not been out here in the field myself, but my colleagues Phil Fralick and Rob Riding have been, there is a large chunk of dolomite, and there's a lot of faults in between, basically where that arrow is. I'll admit that we are probably missing some section in between here. I would love to go back and look at some other spots. So the angle of that arrow looks really steep here, but it could very well be a more gradual pullback down that we are missing. It could even be several dozens of meters that we're missing. You can find out more about that in Phil Fralick's 2015 paper, Beautiful Detailed Sedimentology. So that angle we can't really trust too much. All we know is that there is flooding, there's some gap in time, and then we suddenly have these platform margin deposits. Now going into the periodicity between non-fenestral, fenestral, and crystal bands, I would love to do a little more experimentation or modeling of like how fast these things could grow. I've been reading a little bit, I believe it was Vladdy Alterman's work, who compared different facies and compared the relative growth that he assumed those species could do. I don't have a really good answer for what cycle this is. I don't think it's like a daily tidal thing. I mean, they're huge, but that doesn't quite seem to most fit. Maybe there's some other periodic fluctuation, maybe like current dynamics. I'm not going to get too into detail in what the periodicity might be. Maybe it's years or decadal, maybe closer to years, but the influence might be due to, again, the relative fluctuations of iron concentrations. The more iron you get, that might inhibit fan precipitation, but then more pulses of oxygen. I think it kind of comes back to Raban's question. I think the cyclicity there could very well be due to periodic restriction and then influence of open ocean. I will admit I don't know very much about modern platform cyclicity in like the Bahamas. So if anyone has any questions or comments about that, any insight into how modern reefs cycle over time, that might help us a lot. I hope that helps answer your question.
He's just sent a follow-up. It says,
Oh,
is the structure of microbial mats influenced by tidal, high tide, and low tide based cyclicity?
yeah. I mean, like we see on not talking about individual tides, I'll come back to that. Like we see, like there are broad patterns across Earth history as to where we see different, like subtidal versus intertidal. Like usually they're thinner in intertidal zones, usually thicker and deeper in other zones. But on a tidal, if I'm understanding your question right, if if these are due to individual tides on a daily basis, maybe not, but maybe we're getting more towards like larger tide cycles, maybe not even like the monthly, pardon me, voice is going. Spring and neap tides, perhaps they're larger tide cycles over more yearly or decadal. I'll be honest, I'm kind of spitballing there a little bit. That's one question I would like to follow up on, and I wish I had a better answer for you there, but there does seem to be some sort of pattern there. I don't think it's nothing, but the exact timing still a little bit iffy in my book.
Okay, thanks, Dylan. Maybe I can ask a couple questions about sort of what data you have in addition to what you've shown. Um, I'm curious, you talked a little bit about the plume volcanism, and the plume volcanism. One way for this could be a positive europium anomaly. Did
Mhm.
you calculate check for this?
We did look for positive europium anomalies. We see the ones I remember as having the most strong positive europium anomalies are our columnar ones here
Hmm.
in green. I think I remember looking at that and thinking that if there was a clear, we don't see a clear europium trend, or as clear as we do with iron and yttrium. There's this weird spike in the columns here that I honestly don't have a great explanation for why it would happen right in the middle there. Maybe that's an extra plume. I'll have to double check that. Like if I do find something really crazy, I can get back to you on that. But europium wasn't quite as neat as iron and yttrium.
Okay, cool. My second thought was of whether or not your manganese data, if you have manganese data, correlates with cerium anomaly and your iron isotope composition, because that can really help with the oxidation story.
Right. Yeah, I didn't put it quite here for time, but the manganese and iron, those patterns appeared to be very closely related to each other, as one would expect. There wasn't really too much of a difference. Basically, if we have FeTi and MnTi, they look nearly identical.
Okay, cool. I think Daryl's hand was up next, so Daryl, please go ahead.
Yeah, just one comment about the tides. I thought the original model for this platform was it was basically a pile of volcanics that formed in the middle of an ocean and then subsided. It's very
Mhm.
difficult to get a tide in that type of situation. And I don't remember from Phil's work whether there's any evidence in the very basal
Mhm.
clastics above the fluvial stuff for any tides at all. So you may be dealing with wind seep fluctuations rather than tides. So I have to be very careful about using the word tidal in that setting.
Yeah, I would completely agree. There's in the basoclastics, Sterling, you're absolutely right there. I don't believe there's any facies there that we can point to and say that is a tidal, like clearly tidal beds, maybe once or twice, but not very common. I'd agree. I'm sort of throwing tides out just as what I'm familiar with. Being close to the Great Lakes, I should know more about siege, dynamics and all that, but that is honestly something I hadn't really thought about. So this is perfect. Like any alternate explanations besides tides, I'll write that down right now just to see what we could use. I would completely agree, Daryl. The tides
Yeah.
do not have to be the end all be all for here.
And if you are associated with a large cratonic landmass at all, you should have at least some windblown quartz and material in your carbonate. Do you have it? Did you see any, or
It's
did you look?
very not very much at all. These are very, very pure. Not a lot of quartz at all.
It does seem to suggest it's an isolated body.
I would absolutely agree with that for sure.
Okay, thanks.
Thank you, Daryl.
All right, one in the chat from Dan Zess. Amazing talk, thanks. Steep Rock Lake is a tectonically complicated area. Do you think there's a relationship between the tectonic process and the oxygen oasis?
I think that's kind of getting a little bit as what Daryl is talking about as far as like the initial before the base of the Hogarth Formation. Right, there's this volcanic pile that does come up. I know there's some tonalites deeper down. I believe it is directly resting on tonalite, the basal clastics. I do not believe, as Daryl mentioned, that this is a large, it does not seem to be a large cratonic, that we don't see a lot of like quartz. We don't see a lot of that influence here, except for the very, very bottom. So maybe there was some, and if we've completely detached from it, I'm trying to think of a relationship between the tectonic process and the oxygen oasis. Again, the fact that it is, in my mind, the reason I use this picture of maybe it's too small, but this picture is, in my mind, I really truly visualize this as an isolated platform. But that being said, all of this data comes from one specific point. I'm not going to back all the way up, but you saw that there's large stretches of the steep rock lake that haven't really been looked at, which have also been more recently tectonically faulted. What I think we're seeing here is a thin slice of the platform. I think we're seeing a little bit of the edge here. I think we're seeing a bit of the middle, but we're not seeing a lot of the outer stuff here. And I think can look at the iron to sort of tell us that. Like a lot of what Eroglu's team did here, They found these beautiful curves as far as like the farther out you go, beautiful sedimentary trends here where the facies look that they are deeper and the iron isotopes match that. I think our data is really only capturing this last trend. We did a little bit of Rayleigh fractionation modeling as they did, and we realized it's really hard to do if you only have like the tip of the curve here. So to come back to your question, I think in my mind it's an isolated platform. I would really love to come back and expand this to see if that's true. We're really just looking at one snapshot in time. And one final note, it's somewhat related to this. I didn't have time to put this in. It's more of a public call to action. I mentioned that this lake was drained in the 40s. There was mining. The mining has stopped, I believe, in the 70s, and the lake is filling back up. So those beautiful giant domes that I showed to you will be underwater, I believe, in a couple decades after talking to Phil about this. So, like, I think there needs to be a push to gather as much samples as we can from here and other places. And I think it would be very, very well advised, whether I would love to be in the project, or if you can do it yourself, to get some cores out here. I think some drilling project would be great. There used to be drill cores here. They have all been thrown away as far as we've known. So there's my plug, since it does relate to spatial extent of this. So thanks for listening to that, Dan. I hope that answers your question.
All right, that's it for any questions in the chat or hands. Would anybody like to ask? Oh, Karthik asks another one in the chat. Is there evidence for possible early diagenetic mobilization of rare earth elements? And would this mobilization affect the PRPR star ratios or even the cerium ratios, as is there poor water data in the steep lake? And is there poor water data in the steep lake?
All right. One, I don't believe we have poor water data in the steep lake, but I can answer your first one more confidently, Karthik. I don't have the data here. This is one that is hopefully very close to publication. This is led by Laureline Patry, and it's got all the crew on it and even more. Laureline took data from Steep Rock and from other locations around there, and did exactly what you asked. We wanted to see for certain if these cerium isotopes were real. I mentioned that rare earth elements are typically really good in carbonates, but that's not always the case. You can have enrichments after the fact of certain ones. And so what our team did, broad brushstrokes, is look at lanthanum. We did some different styles of dating. I'll be honest, I wasn't the forerunner on that side of the project, but for the anomalies we see here, and for other earlier cerium anomalies that we see, we do not see any evidence of post-depositional alteration, or that is to say, we don't see any post-depositional emplacement of a negative cerium anomaly. If you're looking out there for what we're talking about, a great paper to look at is Bonnand et al., Bonnand, looking at anomalies from the Barberton that were assumed to be older than 3 billion, but then were shown since to be from the Cretaceous or Paleogene. It can happen. Knock on wood, that will be hopefully published in Nature in the next few months or weeks, more likely. So keep your eyes open for that. Patria et al.
Great. All right. Any other questions?
Yeah, maybe I ask a couple. So Dylan, I was interested in broader your perspective on carbonate platform, and maybe it's not fair question to ask since you haven't been there, but sort of the relationship between Haggard and Elbow. Do you imagine it to be like a rim, with barrier reef being, I guess, Haggard, with this big domal stromatolites, and with sea level, basically this barrier reef just migrate up with in a new position? Or do you imagine it originally to be a ramp on which a sort of elbow was deposited, and with sea level rise, you develop a barrier reef? because it has implication, like if it is barrier reef and elbow is deposited in a lagoon, so when you kind of more protected environment, maybe less nutrients, but when a question comes like, how do you get supply of nutrients from deep ocean towards barrier reef in Archean and Oxyc ocean?
Yeah, that's a great question. To start off with the first part, I believe Phil Fralick's initial model in his 2015 paper, I don't want to completely misquote him, but I think if you look at the diagrams, I think he assumes that there was a barrier the whole time, but it has migrated to a part where we can see now. Essentially, what I've shown you is one strat column, maybe a couple. Looking at what we've seen with our rare earth element data, I think it might be more likely that it was a ramp, since we see very that consistent, flooding over time. And this is, I'll admit, to me, I'm more used to, my background in carbonates is more lake carbonates. So this is really my first foray into the larger microbial reefs. To answer your question, I think, gun to my head, I think I would say that the Hogarth is maybe more like a ramp. Again, there is a big missing chunk of time in the middle that would be really helpful to help bridge the story. And that maybe as the ramp grows over time, we turn into that platform. I need to look more about the specific mechanics that. The nutrient story that you ask, I'll be honest, I haven't thought too much about the nutrients. If you're blocking off how the nutrients get in, I would say that looking at our cycles in the domes between our, more iron rich, or at least, more iron rich, more reducing, and then cycling back to our oxidizing, it would appear that whatever the timing of that may be, whether it's tidal or siege or something else, it would appear that there is some material being brought in periodically, at least, if not over these domes, into these large domal areas. How far it's reaching back into the platform and whether conditions there would be nutrient limited, a fantastic question, which I think would require a more lateral extent to see. But I think at least at the very margins here, we see that there is at least some influence from more open, but potentially more nutrient-rich oceans. I hope that kind of answers your question.
Okay.
There's still a lot to be done. This is the upshot of that, but.
And maybe another question closer to you. So you have a negative cerium anomaly in crystal fans, and like originally, Don Sumner related crystal fans to inhibited effect of iron. So how do you reconcile this sort of oxidative condition that should remove iron from solution, and yet you precipitate crystal fans that seems like require inhibition? So it seems like if you would remove iron by oxidation and release this inhibition, you should allow normal precipitation of carbonate rather than in crystal fans.
If I remember correctly, and it has been a while since I've read these papers, if I remember correctly, the inhibition is a little bit more specific than that. And if anyone remembers, I could be wrong here, that the inhibition for iron on calcium, like it inhibits certain styles of growth, that when you remove, because I'm almost positive that she said when you remove iron, you are more likely to foster growth, right? When you remove that inhibitor, and I don't believe it inhibits initial carbonate precipitation, but it inhibits growth once you have carbonate. So if I'm understanding correctly, let's say we have some carbonates, it's iron rich originally, then we remove our iron. Now we have removed all of that inhibition on the surfaces that then can continue to grow outward. That's how I understood it, but I definitely need to reread those papers. I don't know if that answers your question or not.
Yes, my feeling was that it's higher iron content sort of inhibit carbonate precipitation, lead to supersaturation, and then if you have centers for like pre-existing crystals, or if you have like surface sediment flow that can be used as a kind of template. That's where it starts to grow.
I would completely. I think we're on the same side there. Yeah, that you can have very super saturated waters but just a little bit of iron prevents precipitation. Once you remove that iron, it's still super saturated. Perhaps even more so if we're removing CO2. That's a whole other thing. But I think yeah, it's saturated with iron. Remove that iron, it's still saturated, and now it can feel free to grow. I believe that's the sort of thing that we're seeing, at least here lower down.
Okay. And
Because we definitely, sorry,
do you have
I just
different?
want to note here that
Okay, sorry, go
no,
ahead.
no, yeah, that we kind of see this trend. It's only one spot that we go from higher iron to lower iron here. We're decreasing, but again, we would need more fine scale resolution to determine that. That's my last little point. So, what else did you want to ask?
And last question, do you see any difference in total organic carbon content? Is Elbow more organic rich, or it's all so few
Yes.
little organic carbon? Okay.
We have more organic carbon in, I forget the exact trends, and I don't think it's a nice clean trend, but we typically see more of them in our Hogarth facies, our lower ones down here.
Okay. Okay, thank you.
Thank you very much.
All right, Dylan, one last quick thing before I think it's good time to stop, but Karthik wanted you to restate or type into the chat the paper that you said suggested to keep an eye out for, the one that's coming out in Nature in the next month, you said?
Yes, okay. I'll read it all. That's her last name. In review for sure. It's been bouncing around, not gonna lie, but it feels good for the moment. And I will just mention that as dating the cerium anomalies in the superior craton. I mean, this isn't the exact name, but you can sort of use this to look it up.
Cool. All right,
Okay.
thanks for adding that.
Thank you very much.
Yeah, okay. Well, thanks a bunch. This was really good discussion. It was a really good contribution to this series. Like to see this stuff. So, Dylan, thanks for contributing.
Thank you so much for having me. Again, thanks to Riverside, and thanks to all of you for listening. This was a blast.
All right, everyone, take care and see you further along in future talks.
All right. See y'all.